Okay, welcome to a short video going through question number 4 of the Physics P3 AQA June 2016 higher tier paper. I've put the equation sheet, or the equations you're given, here. Yes, you don't need to remember them, but you do certainly need to know what they're for. So let's not waste any time, get straight into it. So pause the video, read the question carefully, attempt it first, that's the best thing to do. Okay, so if you have paused and read the video, read the question, then the first thing is asking you to, it says figure 6 shows a ray of light going from air into an optical fibre and then travelling through part of the optical fibre. So we can see it going in, bouncing around a bit, okay. Which one of the following pairs of angles correctly identifies the incident and angle of refraction? Okay, so the ray comes in this way, it is then refracted, we've got a normal line drawn on here. Okay, so the angle of incidence is measured from the incident ray, this is the incident ray, to the normal line. So that would be, angle of incidence would be A, so it's one of these two being correct. The angle of refraction is measured from the refracted ray, that's the refracted ray, to the normal line, which would be D. So it's A and D, it's this one. Second part of the question asks you to, the glass used to make this optical fibre has a refractive index of 1.5, which means, more generally, if this is the glass and this is a vacuum or air, if a ray comes in, it will bend towards the normal line, right? It's going to slow down, and the ratio of this angle, or the sine of this angle, and the sine of this angle, sine I over sine R, would give you a value of 1.5. That's what that's telling you. Okay. Calculate the critical angle and give your answer to two significant figures. So again, just because I want to make sure people understand what this question is about, the critical angle is, let's think again, it's similar to this, but you're going in the opposite direction. So again, air, glass, this time you're going this way, and the ray bends away from the normal line. And at some point, right, if you make that angle steeper and steeper and steeper, so if you fire it in even steeper, at some specific point, the refracted ray gets refracted by 90 degrees. That is the critical angle then. This becomes the critical angle. You can use this equation if you're careful and you think about it to determine the critical angle, but actually the AQA have given you a shortcut so you don't have to think about it too much, and you can just use this formula. Okay, so just using that formula, it's a simple case of subbing the numbers in. So the refractive index is 1.5. 1 is just a number. Sine and C is the thing I'm trying to find. So I need to rearrange to make C the subject of this equation. So, several ways of doing this. Actually, I could just invert both sides of the equation, right? So I could flip these two up, and I can also flip this, right? Because you can think of the 1.5 as being over 1. So inverting both sides of the equation would get me 1 over 1.5 would be equal to sine C, and I could draw it as over 1, but I don't really need to. So 1 over 1.5 equals sine C. Again, I could keep this all on the calculator, but I'm going to expand this out just to make sure everyone understands what we're doing. 1 divided by 1.5, if you do that on the calculator, comes out as 0.6666 recurring basically, equals sine C. Okay, and I need to get rid of the sine. So essentially, I can multiply both sides of the equation by 1 over sine C. Sorry, 1 over sine. 1 over sine is sine to the minus 1. So if I do sine to the minus 1 on both sides of the equation, sine cancels this side and I'm just left with C. So I'm going to take, basically on the calculator you press shift sine, which gives you the inverse of sine, and then of the value 0.66. And when you do this, C comes out at 41.818. I did this earlier, so I've written it down and I've kind of can't read my handwriting, but you get this really long number. It says give your answer to two significant figures. 1, 2. So it should be, it's 8 here, so we're just going to round up to 42 degrees. Don't forget your units. Okay, it gives you in the question. Alright, so that's how to do the calculation part. Let's look at the last bit of the question. Short pulses of light. Again, sorry, pause the video and read it and attempt it first. Think about it first. Okay, so again, short pulses of light can carry information through optical fibers. Each pulse is made of a lot of rays of light. Okay, the light rays refract into the optical fibers at different angles when the pulse is sent. The paths of two possible rays A and B are shown in figure 7, and these rays make up part of the pulse shown in figure 8. So we've got two rays, A and B, and the initial pulse, it looks like, so a pulse of light entering the optical fiber has changed when it leaves the optical fiber as shown in figure 8. So it enters like this, one sharp pulse, and it comes out all spread out. Right, pulse of light entering, pulse of light leaving. So why? By considering the paths. The paths, what does that mean? The path. Right, so what path did you take to school in the morning? Your friend got there faster, or your friend got there later. Who took the shortest path? That's what you should be thinking. So by considering the paths of ray A and B, explain why the pulse of light shown in figure 8 has changed as it passed through the optical fiber. Let's go back to the school analogy, okay? Let's say that you've got two brothers, they live in the same house, right? They both leave for school at the same time. Here's the school. Okay, there's the school building. Make sure I can spell school. Okay. Let's say that brother A, they both leave at exactly the same time, right? So you can see, like, from this, you've got this intensity. 1, 2, 3, 4 and a bit. 4.5 brothers left. Whatever you like, okay? Let's just say the first brother took this path, A, and the other brother, being a bit of a naughty boy, went to get himself some silly fizzy drinks first because he doesn't care about his health, right? And then decided to go and have a look at his friends playing some computer game on their mobile phone and hang around here or meet up with someone else and then go to school, okay? So if you time them, right, brother A, the brother that took path A, would have arrived first, so he'd have probably been around here. That's brother A arriving to school. And brother B would have arrived here, right? Now this is only for two brothers, but actually there'd be multiple brothers, wouldn't there? There'd have been brother C, brother, you know, there's lots of rays of light. Brother C might have taken a different route, again, even slower, right? So brother C would have been also up here somewhere, right? And there might have been one sort of in the middle-ish, right? So that would have been accounting for these. So that's why the pulse seems all spread out. They all set off at the same time pretty much, and then they arrive at different times. And you think of them as traveling the same distance, but in fact they haven't. So what I'd be writing here is path A is shorter. Whoops, path A is shorter than B. So since light is moving at the same speed, since light's moving at the same speed, they arrive at different times. Making the pulse more spread out. Spread out in time. Okay, I hope you found this useful. Just for reference, this is the actual mark scheme, but often I find the mark schemes aren't as helpful as having a good old think about what was going on. If you're still finding these calculations difficult, right? If you're still finding calculations on critical angle or anything to do with refractive index, please refer to my videos with practice questions on critical angle. I'll post them in the comments. Okay, I hope you found this video useful. Please comment, like, subscribe and share. Turn notifications on. And I really do listen to feedback, so if there is anything in this video that you didn't understand or you think I could have done better, please let me know. Thanks for watching.